For this problem, we want to find out which of these molecules are polar. So to do this, the big picture of things is you want to start off by creating the Lewis structure, identifying the bond dipoles by using the differences in electronegativity, and identifying the net molecular dipoles based on the molecular geometries. So we start off with the SO3. To make the SO3 Lewis structure, you first find the total number of valence electrons by adding all the valence electrons of the 3 oxygens and the 1 sulfur, and you get 24 valence electrons. So then you want to write out your S in the middle with 3 O's, and you fill in each of the electrons to try to fill all the octets. For this situation, because it does not work perfectly to where you get one bond and then 3 lone pairs on the oxygen while still filling the octet of the sulfur, you must use a double bond on one of the oxygens, and you can see here that there are 3 different equal resonance structures. But in real life, they would all be sharing this bond, and it would actually look like this, where they would have 2 lone pairs and then the shared bond and then the bonds they don't share. So we know that oxygen has a greater electronegativity than sulfur does from the trends in the periodic table where electronegativity gets greater going towards fluorine. So the angle between the geometry of this molecule will be trigonal planar, and all the bond dipoles will point out towards the oxygens because they are more electronegative. And because they are all equal and pulling out, the bond dipoles will cancel each other, and you'll have a net dipole of 0, and it will be nonpolar. Next, for the OF2, for the Lewis structure, you have a total valence of 20, and the Lewis structure comes out to this. The domain geometry is tetrahedral, but the molecular geometry is bent. This is because when you draw the domain geometry, it has 4 domains, so it would be 1 on top, and then the 3 on the bottom. But when you replace 2 of these with non-bonding pairs, it becomes bent. So next, we know that fluorine has a greater electronegativity than oxygen, so the dipoles will be pointed towards the fluorine, and you'll get a net dipole right here going down, and so OF2 is polar. For BeCl2, your total valence is 16 electrons. You have the Lewis structures like this. Now, Be is an octet violator, so you have to be careful here. It's an octet violator because it has less than the amount of electrons to fill the octet, and this is okay because for Be to have a formal charge of 0, it usually likes to have just 2 bonds and no lone pairs. So the molecular geometry for this is linear because the 2 chlorines will be pulling away from each other at a 180-degree angle, and the molecular and domain geometries are the same because there are no lone pairs. And because Cl has a greater electronegativity than beryllium, the bond dipoles will point towards the Cl, and they will cancel each other out, and you'll have no net dipole, which means that beryllium dichloride is nonpolar. So moving on, we have CCl4. Your total valence is 34, and the Lewis structure comes out to look like this. The domain geometry is tetrahedral, and because chlorine has a greater electronegativity than carbon, and because of that, the dipoles point towards chlorine, and since they're all equal and pointing in opposite directions, there's no net dipole, and carbon perchlorate is nonpolar. Finally, we have ozone. Ozone has 18 total valence electrons, and you get another resonance structure, so it could either look like this or this for the Lewis structure, but the real molecule would be like this, where it shares a bond. So the domain geometry is trigonal planar because there are 3 domains, but the molecular geometry is bent because one of these is replaced with a lone pair, and it causes a bent shape. And so because these outside oxygens have 2 instead of 1 pair of Lone pair electrons, they get the negative charge, and the bond dipoles point towards them, and the overall net dipole will be coming right here. Will go down, which means that the ozone is polar. Now, some common mistakes that people make for these is that often they will mix up the Lewis structure, which is really important not to do, because if you get the wrong Lewis structure, your whole problem will be wrong no matter what. Also, it's important to recognize the difference between the domain geometry and the molecular geometry, because although they're sometimes the same, they're not always.